Okay, welcome to Physics 18.3, the last video of the year. We're going to look at application of lenses, and in particular focusing on the human eye. So we want to look at how the eye focuses images and what is meant by nearsighted and farsightedness, and how we could correct them. We're also going to look at a couple of other applications for lenses. Index of refraction. Remember, that's the ratio of the speed of light in a vacuum compared to the speed of light in that particular medium. And of course, the eye has a difference index of refraction than a vacuum. So we're going to talk about nearsightedness and farsightedness. And the properties that you have learned about refraction of light through lenses are going to be used in almost every optical instrument. In many cases, we're going to use a combination of lenses and mirrors to produce images that are either small or far away objects. Generally is what we're trying to bring them closer. Sometimes we actually move objects away from us. So we're going to talk about telescopes and binoculars and cameras and the like. Okay, so let's take a look at the human eye. It basically is pretty much a spherical vessel with a lot of liquid in it. There's a couple of pieces to it. The light that is emitted or reflected off an object is going to pass in, as represented by these red rays. The light passes through the lens, so we got the lens up here, and it ends up focusing back here someplace on the retina. And if you have good eyes, you're going to get a nice clear image back there. And then the cells on the retina are going to take that image. Remember the rods and cones. We're going to take that information and send it to the brain as electrical impulses along the optic nerve, and then your brain basically interprets all that. Actually, the light entering the eye is primarily focused by the cornea, not the lens, because it's this air to cornea surface that gives us our biggest differences in the index of refraction. The lens really is just a kind of a fine-tuning instrument that allows you to see more clearly for both distant and nearby objects. Using a process called accommodation, your muscles around the lens actually pull the lens and stretch it. It changes the shape of the lens just a little bit. You don't really think about it. Your eyes just normally do that automatically. So this is going to focus the eyes. When your muscles are relaxed, you're looking at objects that are distant from the eyes. Basically, if you're asked to relax your eyes, you generally want to look off into the distance. You don't want to concentrate on something close up. When you're reading, your muscles are constantly contracted to be able to focus on those near image. And what happens is that many people don't have a sharp focus of image on the retina. The images are either focused in front of the retina or behind it, and your brain just really can't figure that out then. We will use external lenses like eyeglasses or contacts to make some adjustments, or we'll use like a LASIK surgery that'll actually change the shape of the cornea and the lens so that it focuses correctly. So nearsightedness, what is nearsightedness or myopia? This is where the focal length of the eye is too short. And we got a little video here that we can watch. So it comes in and it ends up focusing before it gets to the lens, and that's no good. So if we put a concave lens in front of it, we could basically cause the rays to diverge just enough so that they end up focusing on the retina. Farsightedness, basically it's focusing behind. Now they call these things nearsighted and farsighted because nearsighted means that even though your eyes, even though it's generally it focuses in front, you could use the muscles in your eyes to get your eyes to focus on things that are close up. So you can read just fine, you just can't see things in the distance. With the other situation where you're farsighted, again, the muscles can't just pull enough to get the lens to focus on the lens when you're trying to read something close up, but things off in in the distance, the muscles will be able to pull the lens around enough just to get it to focus. Similar results is caused by the increasing rigidity of the lens. In other words, the lenses can't get pulled around by the muscles anymore. People who are about 45 tend to need glasses. So the muscles cannot shorten the focal length enough to cause the images to form. So in this case, we can use a convex lens and cause the images to converge just a little bit, and so that they'll end up focusing at the right spot. Okay, so that's basically the eye. A couple other things we can talk about is like telescopes. Now the way a telescope works, again, the rays come in, they basically will get focused at the focal point of the lens, and then the lens, the inner lens, the eyepiece lens, kind of takes it from there. What your eye ends up seeing is rays coming in at an angle, as you see described here. And your eye, then your brain kind of backtracks at and thinks it's looking at an object about here, a large object. So that's what the telescope's doing, is it's bringing that object in. The light is so far away that we can basically consider these to be coming in parallel, and so the lens works. Again, we get an inverted image, but that's fine when we're looking at stars and everything. We really don't care whether it's inverted or not. So we're looking at the virtual image is produced, it's upright and larger than the first image if we put another set of lenses in there. And so that's basically the telescope. We're not going to do too much with telescopes. Sometimes we're going to have to put some combination lens in there to clean up the images, particularly the peripheral color. When you have a camera, again, the reflex camera, we have a lens and an aperture. The light is basically bounced off of a mirror and up around through some prism systems, in through a focal piece, and then into your eye so you could see it. When you release the shutter, the mirror moves up out of the way, and the back of the camera is exposed, whether that's a film, the old-fashioned film, or whether that's a new set of sensors in here, light sensors, that causes the image. But that's basically how that happens, and then the shutter will fall back into place. We're looking at a microscope. Again, we have light coming up through the sample, and there's going to be a couple of lenses. The different lenses then are going to be able to focus it on the eyepiece. So microscopes are used to very small objects, it's kind of along the same lines as a telescope, except that we're looking at things that are really close and really small instead of things that are really far away. That's why we call these compound microscopes, because there's a series of lenses involved. And the real image is produced is inverted and larger than the object. You probably remember that when you move the slide around. If you want to look at something that's up, you have to move the slide in the opposite direction. So the object the image becomes the object of the eyepiece, and then this image is between the eyepiece and its focal point. Anyways, the virtual image is produced that is upright and larger than the image. Thus, the viewer sees an image that is inverted and greatly larger than the original. Binoculars, again, we want the original lenses or the objective lenses kind of spread out, but the other lenses have to be close enough so that you could put one lens in front of each eye. And so what they use is a set of prisms to bend that light around. So the light comes in and it bends out through prisms instead of mirrors. The prisms work just as well, and then direct it through the eyepiece. So each side of the binocular is like a small telescope, and light travels through a couple of prisms. Remember the total internal reflection that we've talked about, and so then the viewer basically sees the image correctly and right side up. Also extends the path of the light, so now we basically get the benefit of that little bit longer path of light between the lenses. Also the separation helps us see things in a more or less three-dimensional view. Okay, so that's it.